Hello and welcome to today's lesson looking at the acceleration required practical for the forces topic in GCSE Combined Science Physics. So what we're going to be doing in today's lesson is we're going to be trying to experimentally verifying Newton's laws of motion with the force and acceleration required practical. Now if you remember in part 1 we looked at how the acceleration of the object depends on the size of resultant force acting upon it. Well, in this lesson, part 2, we're going to understand how the acceleration of an object depends on the object's inertial mass, which it will have. Now we'll then review to look to see how we can collect and analyse experimental data based on a scientific method to verify these relationships. So this links into the specification of GCSE Combined Science in the following part. It's required practical 19, so investigating the effect of varying force on the acceleration of an object of constant mass and the effect of varying the mass of an object on the acceleration produced by a constant force, which falls into the forces topic of GCSE Combined Science. So like we mentioned before, the laws of motion determine the movements of all objects in the universe, and Newton's second law of motion is F equals ma, which is resultant force in newtons is equal to the inertial mass in kilograms times by the acceleration in meters per second squared. So basically it tells us the size of an acceleration depends on both the mass of the object and the resultant force acting on the object, which is the mathematical interpretation of Newton's first law of motion. So this law indicates what the two factors are which affect the acceleration of an object. So the acceleration is directly proportional to the resultant force acting on the object. So if we plotted resultant force against acceleration, we will get a straight line through the origin, because a graph which has a line of best fit, which has a straight line through the origin, indicates direct proportionality, but acceleration is inversely proportional to the mass of an object. Now, just to clarify, the full name of mass in this context is actually the inertial mass of an object. Now, the inertial mass is a measure of how difficult it is to change the velocity of an object or to accelerate. So the larger the inertial mass, the harder it is for an object to change velocity, to speed up or to slow down or to change direction. Now, the larger the inertial mass, the harder it is for an object to accelerate. Now, we know this because if we rearrange the equation, inertial mass is equal to resultant force over the acceleration. So we can actually define inertial mass as the ratio of the force over the acceleration. So like we mentioned before, the larger the inertial mass, the greater the resultant force needed for the same acceleration. The smaller the inertial mass, the lower the resultant force needed for the same acceleration. So the larger the inertial mass, the greater we say the inertia of the object. Now, obviously, this equation needs to be memorized for your examination. You need to be able to use it, recall it, and rearrange it in your examination. But in today's lesson, we're going to see if we can experimentally verify it. So it's very, very common to be used in examination questions. So in our investigation today, we're going to try and find the relationship between the inertial mass and the acceleration for a moving object. So if you can find how they link together, you have learned in this required practical. So to measure the effect of the inertial mass on acceleration for an object experiencing a constant resultant force, you will need the following bits of equipment: a trolley or a toy car, a meter ruler, a pencil, chalk or masking tape to mark intervals, a bench pulley, a string, a stack of small weights, stopwatch and blue tack. So you set up the bench, the pulley, the weight stack and the object as you've done in part 1. You then select a weight for the weight stack that will accelerate the object along the bench and will obviously accelerate it enough to get a noticeable acceleration, but not too quickly that the actual equipment can't be measured. It can't measure the acceleration with it. You then put a 200 gram or 0.2 kilogram mass on the object. You will hold the object at the start point, attach the weight you have chosen to the end of the string, release the car at the same time as you start the stopwatch, pressing the stopwatch lap mode at each measured interval on the bench and for the final time at 100 centimeters, and you repeat steps 1 to 6, placing an additional 200 grams or 0.2 kilograms of mass on the car in each attempt. So as you can see in this diagram, you can see this taking place. Now, what we'll look at is another way in which you can do this investigation, not by using a stopwatch and the humans to do this. Rather, we'll be looking at using a data logger. So what you can do is place a trolley of no mass on a bench attached to a set of known masses with a string and a pulley. Now, the known mass will provide a resultant force downwards, its weight, so that will provide this resultant force acting downwards. Now remember, we calculate weight with the equation weight equals mass times by gravitational field strength, or the strength of gravity. Now, when measuring the known mass, just remember we've got to consider the mass of the hook and of the masses because they're all acting as one in this instance. Now, this will accelerate the trolley of known mass because what will be happening is there's a resultant force acting on the trolley and a resultant force will cause an acceleration. Now, in this investigation, the resultant force produced by the known masses hanging off the pulley is going to be our control variable. This means it must stay constant throughout the investigation. So once you've selected a known mass to hang off the pulley to produce a resultant force, we can't change it in the investigation. Now when the known mass is released, this will cause the trolley to accelerate along the bench. Now as the trolley moves, it'll experience friction, which dissipates energy to the internal energy of the surroundings, which will lead to a degree of inaccuracy in our investigation. Now it's also interesting to note that this effect is actually increased if the mass of the trolley is increased, because if the mass of the trolley is increased, the trolley's weight would be greater, so the contact with the wheels and the bench will be larger, which increases the effect of friction because friction is a contact force. So to remove the friction, in theory, you could carry out the experiment on an air track as the trolley would not be touching the bench, as friction, like mentioned before, is a contact force. So if you remove the contact, you'd remove that idea of friction being generated. Now that would make our results more accurate if we could do so. Now, to measure the acceleration of the trolley, we place a light gate connected to a data logger over the trolley and place a card on the trolley. Now the light gate is connected to a data logger which can calculate the velocity of the trolley. Now as the trolley moves along the bench, the front of the card passes through the light gate. This allows the data logger to record velocity 1. Then as the back of the card passes through the light gate, this allows the data logger to record velocity 2. Now you can then calculate the acceleration the trolley is undergoing, as the change in velocity will be velocity 2 minus velocity 1, and acceleration is equal to change in velocity over time taken. Now for this to gain accurate results, the string mustn't be slack, otherwise some of the resultant force will be used to tighten the string, not to accelerate the trolley. So we've got to make sure our string is very tight. And also the known masses which are producing the weight downwards must not hit the ground before the back of the card passes through the light gate, as it's the masses that are falling to the ground which produces the resultant force. So the fallen masses will produce a constant resultant force as the strength of gravity on Earth never changes. And as the same value of fallen mass is used, this means the resultant force in the investigation is a constant, it's a control variable as we desire. Now to change the mass of the system, the mass of the trolley is varied, not the mass of the fallen masses. This allows the mass of the system to increase, but makes the resultant force stay the same, which is what you want. So we've got to place masses on the trolley as we progress in this investigation. So the acceleration is measured for different trolley masses. So you can place different masses on your trolley. Now it's recommended you measure the acceleration of the trolley when 0.20 kilograms, 0.40 kilograms, 0.60 kilograms, 0.80 kilograms, and 1.00 kilograms are added to the trolley. Now, as we're only observing a trend here between mass and acceleration, the mass of the trolley does not need to be considered because it's the same for each reading. So in essence, that mass of the trolley is going to be a constant for all the different values. So adding on masses will actually cause that change, not the mass of the trolley itself. However, if we wanted to derive an experimental value from the investigation, say we wanted to work out a quantity, such as, for example, the resultant force, the mass of the trolley would have to be added to the masses placed upon it to work out the total mass in motion. So just remember, if you wanted to work out a value, okay, a numerical value, you've got to consider the mass of the trolley and the mass of the masses added onto it. Now, by adding masses to the trolley, the whole mass of the system is increased, but the force applied to the system stays the same. Now, this in theory should lead to a decrease in acceleration as A equals F over m. So if m is getting bigger for the same F, you're going to have a smaller a by looking at the mathematical equation. Now, once you've done your experiment, you should plot a graph of average acceleration on the y-axis against the mass placed on the object on the x-axis, and then draw a line of best fit on your graph. Now, you'll draw your line of best fit in, but it won't be a straight line through the origin. It should be a curving line of best fit downwards as shown. Now, this shows the two factors are not directly proportional, rather they are inversely proportional. Now, there's another way to show inverse proportionality, and that's not to plot acceleration against mass, rather is to plot acceleration against 1 over mass. Now, if you did that particular graph, you would then get a straight line through the origin. So if you plot a value against 1 over the other value, inverse proportionality is shown by a straight line of best fit through the origin. Now, what have we learned in today's lesson? That the acceleration of an object is proportional to the resultant force acting on the object, but inversely proportional to the mass of the object. These two factors are combined in the equation, Newton's second law of motion, F equals ma, where F is the resultant force in newtons, mass is the inertial mass in kilograms, and acceleration is given in meters per second squared. Now, also in today's lesson, we should be able to see how we can do an experiment to verify this particular equation. Now, if we're being successful and we've learned in today's lesson, we understand how the acceleration of an object depends on the object's inertial mass, which it has, and we can review how to collect and analyze experimental data based on the scientific method. I hope you've enjoyed today's lesson looking at the acceleration required practical, and you understand how acceleration can be linked to the inertial mass of an object and can be measured experimentally. Thank you very much for listening to today's lesson, and have a lovely day.